Hey, this is Chris Sullivan. I'm a PhD student at Michigan State University where I work at the National Superconducting Cyclotron Laboratory. And I want to tell you a little bit about a project I've been working on in the development of evolving neural networks and most recently employing general purpose GPU acceleration to parallelize these guys. This is part of, at least the parallelism part is part of the end of a course project on algorithmic techniques for scalable many-core computing, which is a collaboration with the University of Illinois, where we're able to sort of in a timeshare kind of way work on the Blue Water supercomputer. So shout out to them. Thanks a lot. It's a great course. I want to tell you a little bit about artificial neural networks to start. So what is a neural network made up of primarily? Primarily, as you can see, it's nodes and connections. But in a little bit more detail, what is a node? So a node is simply something that takes an input value, so a number, a float, all right, and it can take many such inputs from many different connections, many different prior nodes. It then evaluates an activation function with this input as its argument, and this activation function is essentially just some kind of monotonic function which represents activation. So this is where you get the idea of a neuron in a neural network, where this could easily be a step function, or it could be some kind of logistic sigmoid, or a hyperbolic tangent. But for some values of the input, some more negative values, your neuron does not fire. The output might be 0, and for other values of the input, it does fire, and you might get some kind of output such as 1. And in whatever the result of that operation is stored in the output. Connections are pretty easy also. They just connect one node to another, and you can see just a bunch of different connections here, and the boldness of the arrow here is just meant to represent what's known as a connection weight. The idea is that you take the output of a node and you multiply it by its connection weight, and you add that value as the input to the next node. All right, so that pretty much finishes it up for the basic components of a neural network. So let me just show you the simplest possible network one can construct with such components. So this is what is known as a single layer perceptron. Here on the left you can see a input layer. So this is a single layer of inputs which take inputs x1 through xn, and they're transformed into a single output t of x, where x here is a vector, and the w's here are all the weights of each of the connections. In order to evaluate this network, we just take t of x, which is just the activation function I mentioned earlier, in this case a logistic sigmoid shown here, evaluated at the values of w0, which is just a special node, which I haven't mentioned. It's just a bias node. It's another type of input node, and the idea is that instead of taking an explicit input, a bias node always returns a constant value. So in this case 1, and it has the connection that connects the bias node to the output is w0, and it can vary like any of the other weights. So it's this term plus the sum of all of the individual input nodes times their connection weights. And in the end, we just take that quantity and we pass it through the activation function, and that's the output of this neural net. Adding one layer of complexity to the single layer perceptron, we can get a multi-layer perceptron. So all we need to do is add in an extra layer of nodes known as a hidden layer. And just as we did before, we have again evaluations starting with the inputs coming on the left from the input layer you can see here, and those input nodes are fully connected to the hidden layer, which you can see here. And by fully connected, I just mean that each input node is connected to each hidden node. And this is sort of a typical what is known as a feed-forward neural network, where each of the nodes in the prior layer are fully connected to the nodes in the next layer, in the consecutive adjacent layer. And again, each of the connections have weights w's. Now in this case, we have indices for each of the input nodes and each of the hidden nodes. So this is w11. In this case, you can see we only have this last connection here. That in the last connection, you can see there's only one connection from each node to each output node, so that there's no ambiguity, so we still just have one index. So to evaluate this network, we should start by evaluating the first layer. So the first layer, we can say this hidden layer, the values of h of x are just what we saw before. It's a logistic sigmoid evaluated at the weight, the bias node, plus the sum of the weights times the input values on the input nodes here. And this is the sum over all of the input nodes. And then we have an h of x value for each of these hidden nodes. And so then we calculate t of x, where it's exactly identical to this last evaluation. Again, sigma activation function being applied, but this time the sum is over the values of the hidden nodes, which are just these h's that we just calculated. So adding another layer really doesn't increase the complexity very much. Now that we're able to evaluate our network in a fairly straightforward way, the question is, how can we improve our network's accuracy at reproducing the problem at hand, or to reproduce the outputs that we'd expect? That is, how can we train our network to reproduce true output values given some input values that we specify? And in order to do this, we need a set of training data. So that is, data in which we have both the inputs and true outputs. So for a given set of data x, we have the output values y. And then we can define some error function, and that is the difference between the true values of given the input values x and the output values of our network. And so in this case, I just defined an error function, which is y minus t squared here. And the question is, how do we minimize that error with respect to the connection weights of our network? And this is just a simple calculus problem. That is, we just take the derivative of the error function with respect to our weights, and we find the differential quantities of each of the connection weights that we need to add back into the weights in order to minimize this error. This roughly sums up the idea of backward propagation of errors, but it's not the only way of training neural networks that's popularly used anyway. There are other methods, and one such method is known as neuroevolution, or the evolution of training weights, or the evolution of weights. That is, for a given set of training data, you know the outputs again, and from that you're able to evolve. You essentially start, instead of with one network that you're training, you start with a population of networks that all have essentially randomly generated weights. And from that random population, you're able to pick the networks which have the best fitness, or they have essentially the minimum error. And then you allow those networks, only the networks which have the best error, you can pick half of your population, you'll only allow those networks to reproduce. And so then you allow there to be weight crossover, that is the crossover between connection weights in different networks, as well as mutations to occur. So it's, rather than training, you're allowing essentially the networks to evolve towards the answer, or evolve through the problem space in a Monte Carlo-like way. So there's some drawbacks to the standard artificial neural network techniques I've been describing, and they're primarily having to do with the fact that there are a number of free variables that are not really adjusted as part of the training. For instance, in the backpropagation, there's no real, there's nothing that's actually adjusting the learning rate. That is, how much you adjust the weights in each step in order to converge towards a solution, because that's obviously going to affect the speed at which you converge to a solution, but also the reliability of the solution that you actually reproduce, whether or not you get stuck in some local minima of the problem space, or you actually find the true solution, the true global minimum of the solution. And the other issue is that through standard techniques such as backpropagation and weight evolution, standard layered neural networks, they enforce a specific type of network, or they enforce a specific network topology on a problem. And that is that you have to know from the beginning the choice of the topology that best fits the problem at hand. And that's rarely obvious. It's rarely obvious to know whether or not a network with two hidden layers, or a single hidden layer with more nodes, etc., or a hidden layer with a different kind of activation function. It's rare to know whether from the beginning which configuration or network topology best solves that problem. Let me just give you an example. So an example in this case, I'm showing you the exclusive OR operator, or the XOR operator. The XOR operator functions in the following way. You have there's four inputs that you can give it. You can give it 0, 0, which produces 0, 0, 1, which is produces 1, and this is the exclusive OR So 1, 0 also produces 1, and 1, 1 produces 0 as well. And so you can see anytime that the values of the inputs are identical, the output anytime the inputs are identical, the outputs are 0, and anytime the inputs are differing, the output is 1. And the drawback with regard to the topology is simply this. If we have these 3 networks on the side here, where all 3 of them have 2 inputs and 1 output to match the XOR problem, the question is, how many hidden nodes in our hidden layer should we use? Should we use 3, 2, 1? Should we use multiple hidden layers? What about a network which has an extra connection like this, where it actually bypasses the hidden layer and goes straight to the output network? Using standard artificial neural network or layered network techniques, it's difficult to answer this question, and this is not something that is learned in training. So the only way you are able to actually determine this is by putting the burden onto the user. And you essentially have to try each of the different cases and decide which one gives you the better result and converges more quickly. So let me introduce you to another technique of evolving neural networks. I mentioned a little bit about neuroevolution earlier. Now I want to tell you about the NeuroEvolution of Augmenting Topologies, known as NEAT. This is a method developed by Kenneth Ostanley and Risto Maiekulainen, and the idea behind it is that instead of just evolving only the connection weights, we also can evolve the network topologies via mutations and crossover, or otherwise known as reproduction. So let me tell you a little bit about this. So the idea is that there are a set of a few primary mutations, and the networks are represented as genomes. So on the top, I show you a network. So here you can see a network with 2 inputs, a bias node, and a single output node. So it's a minimally complex network here. And the genome is below it, represented by a bias from node 0 going to output node 3, and the other connections as well. One mutation that exists in NEAT is known as the add node mutation. Okay, so we have split the connection going from 1 to 3 by adding a new hidden node and adding 2 new connections. And you can see in the genome representation below, the old connection that connected node input 1 to output 3 is now disabled, though it's still part of the genome. It's just no longer being expressed. And we now have 2 new connections as well as a new hidden node. There's another type of mutation known as the add connection mutation, where you can see in this case we've added a new connection where we go from our prior network to a network that now has a connection from node 2 to node 4, shown in red here. And again, we update the genome. And in addition, you can also have an adjust weight mutation, where the weights are randomly permuted, or rather the connection of a specific connection is randomly permuted within some range that you set. So these represent different structural and weight mutations that can occur every generation. In addition to these, NEAT also allows for topological reproduction between networks. That is, where 2 networks can be crossed against one another, and the structure of both networks can result inside the offspring, or the child network, from 2 parents. One thing that makes NEAT unique among other neural evolution or genetic algorithms for the evolution of neural networks is its proposal to use what's known as historical innovation for network crossover. So the idea behind historical innovation is that as a network develops and adds new connections and new nodes, so as if we started with the base network just 0 to 3, 1 to 3, and 2 to 3, as a new node appears and these new connections appear, and likewise for this parent here, as this occurs, we actually keep track of the order in which they occur. So if we come down here and look at parent 1 and look at its genome layout, we, in addition to having the connection, have an innovation marker here. And so connection 0 to 4 was the original progenitor connection between 2 nodes. And then there was a connection between 1 and 3, and a connection between 2 and 3, and a connection between 1 and 4, and then 4 and 3, etc. And the number here indicates the generation in which the next connection came about, or the ordering, in other words. And so by using these historical markers, we're able to actually make a good comparison between one network and the next network. Because if, for instance, a certain structure has developed in a network over a period of generations to solve some specific problem, like the example before was the if statement of some kind, we can now compare the genes of the other parent and their historical evolution, or the generations in which each of these connections came about, and therefore understand that if a connection is identical between two networks, and if it came about in the same generation, then it is historically the same. And so if we find structures which are historically the same, they all can be brought over into the child network during crossover. Another unique aspect of NEAT is the utilization of speciation in order to preserve new structural mutations or innovation. The idea is that if you have some set of networks that look something like this, which are all topologically identical, and then all of a sudden you have a new network evolve which looks like something like this, this extra connection that's been evolved in this network here initially is not going to be well optimized. Whereas these networks might have had many generations to converge or train their weights to best solve the problem at hand, this new connection's weight is not going to be optimized. And so this network is likely going to do poor relative to these immediately or right away. And so the idea behind speciation is that if we protect networks through speciation, then when we go to determine which networks move on to the next generation and which ones die off, we cull on a species level. So we decide that in this species that these two will be removed if we're doing like a 50% culling rate, for instance. And because there's only one network in this species B here, it is able to continue on to the next generation. And eventually it will be able to train, given enough time, this new connection to be comparable to these. And in fact, because this is topologically different, it actually might be able to solve a problem that these couldn't. So using speciation, we're actually able to protect new innovation and ensure that, much in the way regular evolution does, that new mutations are actually able to be beneficial to a network. And so what I want to tell you about now is some improvements I've made on the NEAT algorithm by utilizing parallelization, and specifically parallelization on the GPU. So just a quick plug here, I'm the lead developer of a library of neural networks known as Entendre. And this is an open source code that's available to be forked on GitHub. I've recently been focusing most of my efforts in the development of the NEAT portion, what I've been describing to you today. And so let's dive in a little bit and look at this code specifically and how I've gone ahead and parallelized it on the GPU. So what I'm showing you here is the basic layout of Entendre, where the CPU code is on the left and the GPU code is on the right, in yellow and green respectively. So let's just go ahead and focus over here on the left for a moment. So each of the boxes in this diagram is sort of meant to, the size of each of them is sort of meant to give you an idea of the amount of time that they take relative to one another. Okay, so in a NEAT population of networks, we have two main components: the generational turnover, or the reproduction and moving from one generation to the next. And in the second part of the code, we have the evaluation part, where we're evaluating the neural networks. So in the generational turnover, you start with a set of genomes in your first iteration, and from those genomes, they essentially encode the genes of all of the neural networks. And so you're able from these to generate the neural networks, and then you evaluate the neural networks on the CPU serially, and then the output of those neural networks then goes into a fitness function, which determines the fitness of each of the neural nets. And then based on those fitnesses, we go into a speciation, mutation, reproduction phase, and then that outputs a new set of genomes. And from that new set of genomes, we generate new networks, and that ends that generation, begins a new generation for which we evaluate them again. So my first implementation of Entendre on the GPU is what I'm calling a direct one-for-one evaluation. And so what that means is that for every neural network, I copy it over to the GPU, I evaluate it, I take the evaluation or the evaluated outputs, copy them back, and then that's everything that's being performed on the GPU. And so each thread on the GPU is tasked with evaluating a different neural network. All right, so instead of evaluating them in the CPU in this case, we just pass them off to the GPU. And again, I show you the size of this GPU box here is meant to imply that it actually does give us a speed up. So let's dig into that. In order to run these comparisons, though, I use the NVIDIA Tesla K80 GPU, which is housed at the High Performance Computing Center at Michigan State University. So here I'm showing you the speed up as a function of population size for our neat neural networks. And this is the speed up that we see for evaluating all of these networks on a GPU. So this time on this axis is just the average amount of CPU time that it took to evaluate a neural network. And that's divided by the amount of time taken to evaluate on the GPU. So each colored line represents the variance in the network topologies between the different populations. So in the case of the red curve, the average number of connections in the networks in this population was 7 with a variance of plus minus 4. And in the blue and the green, the number of connections were around 55, so much larger networks with a variance of plus minus 33. And so in this case, you could see that the divergences, or rather the networks, are very different in this case. In some cases, you could have networks with only 10 connections. In other cases, networks with 90 connections or so in the extreme. And so kind of what we would expect if you look at the case with the average number of connections being rather small and only a few number of connections difference between one network and the next, you can see that the performance is actually quite good. Even from just 1,000 networks, we already have an enhancement from evaluating on the GPU. But as you increase the population size to 16,000 or up to close to 1 million here, you can see in almost all cases we've increased our speed up relative to the CPU. On the other hand, if we compare with the cases in which the networks diverge from one another more significantly, you can see that while there still is a speed up, the speed up is limited significantly. And this is coming exactly from control divergence in the GPU. Because the way we're doing this is that each thread is evaluating its own network. And if one network has many connections and another network has few connections, then each thread has a different amount of work, and because of the vector processors on the GPU, will actually create a substantial amount of control divergence. One significant issue that I ran into, in addition to the control divergence, was the memory I/O between the host and the device. And that's having to do with the fact that each of these are stored as arrays of the structures, or arrays of genomes and arrays of neural networks. And the shortcoming of evaluating an array of structs population, that is an array of neural networks, is that there's a large number of small memory transfers that have to happen. And so if I'm taking every network and copying it over, and then each network has its own inputs that I have to copy over, then I perform the evaluation, and then each network has to have its outputs copied out, that's a lot of mem copies that are happening. And a lot of small mem copies actually add up to be a huge performance hit. So what I want to show you here is a picture on a plot of the time transfer, the amount of time it takes to transfer a certain amount of data as a function of the megabytes per transfer. Okay, so this is a nice plot from Michael Boyer of the University of Virginia. And what you can see is that at around these small transfer sizes, the time to transfer is roughly constant. And we have here roughly 200 bytes to transfer a single network across, plus its inputs and outputs. And that means we're sitting about here in the evaluation time, which is about 0.01 milliseconds. But this is multiplied by the number of networks in the population. And so, as I showed you a couple slides back, if I have a 2 to the 14 population or greater, this is clearly going to be a huge number. So 2 to the 14 networks is roughly 16,000 neural nets, so 16,000 times 0.01, and you can tell this is going to be the dominant factor pretty quickly. So allow me to summarize the drawbacks of the one-for-one evaluation that I've seen so far. The three issues that have held back the performance are: one, there's a large number of memory transfers that become the dominating factor because I'm having to copy each network over individually and evaluate them and then copy out the outputs individually. Two, there's no benefit from memory coalescing because this is an array of structures that we're copying, and so each thread is loading in the input nodes to start from different nodes, different networks that are spread across the GPU. So we don't make any benefit we don't get any benefit from memory coalescing. And finally, there's control divergence from the differing network topologies. So these are the three things that I would like to attack in my next implementation. So just to give you an idea of what that is, what I would like to do is to restructure the population of neural networks, that is an array of structures or array of networks, into a network population or a struct of arrays. And the idea is that instead of having a GPU focus on each of these individual networks, here I'm showing you identical networks. Of course, they are not necessarily after several generations of evolution. But instead of having one thread handle each network, instead, I will consider it as though in each of these networks is actually just one large network. One network with 1, 2, 3, 4, 5, 6, 7, 8 inputs and 1, 2, 3, 4 outputs. And then the idea is that we can group all of these networks into, or the connections of all of these networks into sets of connections which can be evaluated in parallel. So for instance, all of these connections have to be evaluated before all of these connections, right? So the idea is that I group all of these connections together and can perform the evaluation of each of those connections in parallel on the GPU, and then I can perform the evaluation of these in parallel on the GPU, etc. And once all of the evaluations are done, we just copy out 1, 2, 3, 4 values, and we do that in a single memcopy. And the same is true here. When we copy in, we do a single copy in which brings in all of the input values at a single time. And so this is clearly advantageous because now that we're storing things as a struct of arrays or a struct of connections and a struct of nodes, for instance, we actually will be able to gain benefit from memory coalescing because the connections will all be in contiguous memory space. In addition, we won't have the control divergence problem that we had before because we'll have a single set of connections which can be evaluated independent of one another. And finally, because we've restructured our problem into a single network population, we only need to make a single memcopy in for the inputs, a single memcopy out for the outputs, and a single mem copy of the entire network over the GPU. So this drastically reduces the number of memory transfers down to just 3 per every neural network generation. And so as you can see here, this new method addresses each of the drawbacks of the one-for-one GPU evaluation I've described before. And I expect these changes to give a significant performance boost to the evaluation of these evolving neural networks on the GPU. So if you're interested at all, head on over to my GitHub page where you can check out Entendre and apply it to your specific problem if you want. I'm always accepting pull requests, so you can fork the repository and continue some development also if you're interested at all. Otherwise, appreciate your time and thanks for watching. Hope you enjoyed it.